so that the answer should be 6. So there is a value there if n is 1. 4 times 1 plus 2 is equal to 6 pi electrons. That's why benzene, okay, and related compounds containing benzene are aromatic, like phenol, benzoic acid, benzaldehyde, aniline, toluene. All of them are aromatic compounds. Now let's look at these three examples here: pyrrole, furan, and thiophene. Okay, why they are also considered aromatic? Okay, let's check. Now, if we're going to analyze pyrrole, for example, this is nitrogen there. Now, if you notice, only the 4 carbons have double bonds. So these are the sp2. Your nitrogen there, if we're going to generate the formula, this is the central atom. You have 3 sigma bonds, AB3, and you have lone pair, so that is trigonal pyramidal, no? And because there are 4 electron pairs, your nitrogen here is sp3, which is your central atom, and not sp2. It should be sp2, okay? So why is this aromatic? Okay, the answer to that one is due to resonance. Okay, it is not aromatic at the first glance. It is sp3. However, the lone pair will not stay here completely. This will delocalize. Okay, so when that lone pair delocalizes, this pi electron will also delocalize, generating a resonance structure. Okay, in which the single bond nitrogen will become double bond. And look, it's already a double bond. So once you have a double bond, the atom becomes sp2. Okay? And originally, you only have 4 pi electrons here because there are 2 double bonds. But then, when the lone pair here is delocalized, it becomes a pi bond. So if you're going to count now, you have already 6 because the lone pair becomes a pi bond. So it will follow the Haeckel rule. It is sp2 and it is cyclic. So that's why it is aromatic. That goes with furan, which can also delocalize, thiophene, which can also delocalize. So that's why they are all aromatic compounds. Okay? So you have to take note of the 3 important requirements. So let's check this example. Okay, you have this, and you have this one there. Okay, so you have a double bond here, double bond, double bond, and then you have double bond, double bond, double bond. Okay, the first one is 1,3-cyclobutadiene. The second one is 1,3-cyclopentadiene. And the third one is 1,3,5-cycloheptatriene. Okay, so let's check the first one. Okay, if it is aromatic. Okay, it is cyclic, so check. Second one, are all the carbon sp2? Yes, because you have all the double bonds there. So these are all sp2 hybridized. Does it follow the Haeckel rule? Well, you have 4 pi electrons. Okay, so if you're going to use the formula 4n plus 2 to come up with 4 pi electrons, there's no values for n, as you can see, no? Because if n is 0, the answer should be 2. And if n is 1, it should be 6. So there's no value for n that will result to 4 pi electrons. So that's why cyclobutadiene is classified as anti-aromatic, meaning against aromatic anti-aromatic. Okay? Now, because it violates the Haeckel rule, no? Now let's go to the second example. Okay? It is cyclic. Okay? Number 2, are all the carbon atoms sp2? No. There is one carbon here that is sp3. Okay? So therefore, sa second requirement pa lang, it violates na, no? So not all the carbons are sp2, so we call this non-aromatic, okay? Because it violates number 2, no? So it is non-aromatic. Now let's go to number 3, okay? Again, it's cyclic, so that's fine. Number 2, you have, here you have number 3, you have 6 pi electrons there as indicated in the structure. So it fits, okay, the Haeckel rule, 4n plus 2. We have an answer for this one. No? If n is equal to 1, you have 6 pi electrons. So this is fine. This is fine. Now we have a problem with number 2 because again, this hydrogen, this carbon is sp3. So this is also classified as non-aromatic. Okay? Because not all the carbons are sp2 hybridized. Okay? So that's how you determine acidity. Aromaticity. Okay? So, why I discussed this one in relation to acidity? Okay? Because there are, hydrocarbons are not acidic. Unless that hydrocarbon, like CH, is adjacent to a double bond. Because this one can delocalize, making this one acidic. Okay? But there is another case. Okay? Aside from this case, sigma electron delocalization, which will make the hydrogen acidic, there is another case, and that is aromaticity, that will make the CH acidic. Look at this case. That is cyclopropene. This is cyclopentadiene. And this is cycloheptatriene. They are the hydrogen here, okay? Look at the hydrogen here, okay? You have hydrogen, hydrogen, and this hydrogen, hydrogen, okay? Those are sp3CH, okay? But they can undergo sigma electron delocalization. See? That is sp3CH. They can undergo sigma electron, sigma electron, sigma electron delocalization. Okay? So therefore, there is a possibility for this hydrogen to be acidic. Okay? But, okay, there is an additional factor. Okay? Some of these hydrocarbons are not completely acidic. Some of these are basic, okay, while the other one is acidic. So the question is, which one do you think is acidic and which one is basic? Acidic if it is release H+, because that's the symbol for acidity. Basicity if it will release H-, because H- is called hydride, okay? And hydride means the hydrogen is basic. If it is H+, the hydrogen is acidic. Okay, so here, in the first example, cyclopropene, okay? If the hydrogen will be released as H+, the resulting compound Okay, cyclopropene will have one remaining hydrogen and a lone pair because only hydrogen is removed. So that lone pair will be left in the carbon. So your carbon will be negatively charged because the lone pair will be negative. Okay. If the electron of carbon will be carried by the hydrogen, you will end up with a double bond here, hydrogen 1 again. But since the hydrogen is removed as H minus, your carbon will become carbonium. Okay? Here, a negative carbon is called carbon ion. There. A positive carbon is called carbonium. So the question now is, in what ion your cyclopropene will be? Will it be in the carbon ion form? Because if it is in the carbon ion form, it means to say that your cyclopropene is acidic. Okay? But if it is in the carbonium ion form, it means to say that your cyclopropene is basic. Okay? So which one do you think will be released by cyclopropene? H plus or H minus? So, papasok yung concept ng aromaticity. Because aromaticity plus means stability. Because in aromaticity, we can generate a lot of resonance structures, okay? Making the molecule very stable, no? Very stable if it is aromatic, okay? So, here, which of these two now is aromatic? Is it the cyclopropene carbon ion or the cyclopropene carbonium ion? So we have to check using 1, 2, 3, okay, criteria. First cyclic, so both passed, okay. Is it the flat? Well, carbonium ion is sp2. There's a double bond, they are both. How about the carbon ion? Well, the lone pair can delocalize, can generate resonance structure. So if we draw the resonance structure, this one will become double bond, right? And the lone pair will be here, okay, which is our negative, okay? So fine, the carbon also becomes sp2. Now let's go to the Haeckel rule, okay? The Haeckel rule is 4n plus 2. Now in carbonium ion, we only have 2 pi electrons. So n here is 0. But here in carbon ion, the pi electron is not 2. It is 4. Because the lone pair becomes a pi bond. Look at that. That lone pair there becomes this one. Okay? And you have the pi bond becomes the lone pair. So all in all, you actually have 4 pi electrons here, which is not aromatic. So therefore, your cyclopropene, okay, will release an H minus because the resulting ion will be very stable. It will be aromatic ion. So therefore, your cyclopropene is basic in this case, no? Kasi it will release an H minus to become aromatic. So therefore, if you place cyclopropene in acidic medium, it will be very soluble because acid will react with the base. But if you place cyclopropene in basic medium, it is not soluble. Okay? Now let's look at cyclopropene. I mean cyclopentadiene. Okay? Let's see if this is an acidic hydrocarbon or basic hydrocarbon. Again, this is not aromatic due to the sp3CH. So the question is, will this release an H plus? Because if this will release an H plus, your cyclopropene will become, your cyclopentadiene will become cyclopentadiene carbon ion, or you call that cyclopentadienyl carbon ion. The lone pair is left because H plus is removed. So you have the negative there. But if this one will be removed as H minus, okay, your cyclopentadiene will become carbonium. You have hydrogen there, and this one becomes carbonium. Okay, so which one? So use the concept of aromaticity to answer this. Whether your cyclopentadiene is acidic or basic. Okay, so if you notice here in cyclopentadiene carbonium ion, okay, all the carbons are sp2 because carbonium is also sp2. But you only have 4 pi electrons here. Okay, so it doesn't follow the Haeckel rule. Now look at the other one. If cyclopentadiene will release an H plus, the lone pair will delocalize. This will delocalize, generating a resonance structure like this. You have double bond here. The lone pair will become a pi bond, and the pi bond will become a lone pair. Okay? So look at this one here. Okay? You have now all the carbon atoms are sp2. This is already sp2 because of resonance. And the number of pi electrons is increased from 4 to 6 due to pi electron delocalization. So therefore, cyclopentadienyl anion this is negative, right? Is aromatic. Okay, so therefore we can say that cyclopentadiene is acidic because it has to release the H plus dahil yung resulting carbon ion niya ay aromatic. So look at this. Cyclopropene is basic while cyclopentadiene is acidic. Okay? Now let's look at cycloheptatriene. See if you know how to analyze this one. So if we go to cycloheptatriene, you already have 3 pi bonds, so that follows the Haeckel rule. So we only have a problem here. Okay? So again, if this will release H plus, the lone pair will be left. So you have double bond here, double bond, and you have the lone pair. Okay? And take note that lone pair will delocalize. So there will be an additional pi bond. Okay, so your pi electrons will be 6. Whereas if this one will release an H minus, okay, you will end up with this cycloheptatriene. Double bond here, double bond, and this carbon will become carbonium. See? You only have 6 pi electrons here, whereas here, you have 8 pi electrons. So this will be aromatic. So therefore, your cycloheptatriene is basic. It will release an H minus to become aromatic. You see? Okay? We're able to predict acidity and basicity of hydrocarbon using the concept of aromaticity this time. Okay? Now let's go to the main basic compounds in organic compounds, okay? And these are the amines, okay? Amines are basic compounds, okay? So, we use the concept of Lewis, okay? That bases are electron pair donor, okay? So, the more they donate electrons, the more basic, okay? And these are the amines, no? Amines are basic compounds. We can classify them as primary amine, okay? If there is only one carbon attached to the amino group, if there are two carbon attached to the amino group, then we call that secondary amine. Like this one, this is secondary amine. And if you have three, then that is tertiary amine. Okay? So if you notice here, okay, we can correlate this with ammonia, which is an inorganic base. Okay? So here, take note that electron pair. All of this have electron pair to donate. So the more, the greater the ability to donate electron, the more basic. Okay? So if you compare the basicity of ammonia and the primary amine, okay, your ammonia is less basic. Why primary amine is more basic? Due to the presence of alkyl group. Alkyl group are always considered electron donating group. So they can increase the electron density of the lone pair, making it capable of donating electron. Electron donating group will increase the ability of the nitrogen to donate electron, okay? So, the greater the ability to donate electron, the more basic. That's why methylamine is more basic than ammonia. So, if we follow that trend, we would also expect primary to be less basic than secondary amine, because in secondary amine, there are two methyl groups that will increase the electron density, okay, of secondary amine. But if we follow the trend for tertiary amine, we would expect tertiary to be the most basic, okay, right? Because there are three electron donating groups. However, that is not the case experimentally. It turns out that your tertiary amine is less basic than the primary. So what happens here? Why tertiary becomes less basic than secondary, less basic than primary? The reason for that one is that there is another structural effect that comes in, and that is steric effect or crowding. Okay? So you have the alkyl groups surrounding the nitrogen. Take note that the lone pair has to interact with an acid in order to be considered as a base. Okay? This has to interact with an acid. Okay? And if the acid cannot interact, even if nitrogen has a higher electron density because of the three methyl groups, but then the hydrogen cannot approach the lone pair because of crowding, then it becomes less basic. And that is what happened to the tertiary amine. That's why it is less basic than primary and secondary. So if you're going to arrange the three, then tertiary amine will be less basic than primary. Primary will be less basic than secondary. in that arrangement. Okay? Now, we also have aromatic amines, no? Like for example, aniline is an aromatic amine. The basicity is also focused on that lone pair. Now compare that with cyclic amine, like cyclohexylamine. There is also a lone pair there, okay? However, which lone pair is more available to interact with the acid, okay? Is it the lone pair of aniline, okay? Or is it the lone pair of cyclohexylamine, okay? Now you have to look at the structural effect now, okay? If the lone pair is adjacent to a double bond, this can delocalize. So therefore it will disappear from the nitrogen and making it less available. If we're going to write the resonance structure here, okay, it will look like this. That's why it's not available anymore. Okay, the lone pair is lost. It is now in the pi bond. Okay, whereas here, it cannot delocalize because it is not adjacent to a double bond. So the lone pair can easily interact with the acid. That's why aromatic amine is less basic than aliphatic amine. Okay? Now again, for aromatic, we can put substituents. Okay? So what will be the effect on the basicity of aromatic amine? Okay? If you're going to place substituents here, okay? So generally, if you have electron withdrawing here, okay, and compare that with electron donating, this is opposite to that of acidity, no? In acidity, electron withdrawing increases acidity, electron donating decreases acidity. But here, we are talking about availability of the lone pair. So if there is a group that will withdraw that lone pair, then we would expect the basicity to decrease because the lone pair is no longer less available. But if there is a group that will donate, then it will make the lone pair more available and therefore more basic. So therefore, if you have NH2 here, okay, and you have an electron donating, like methoxy group here is an electron donating group, and you have NH2 here, but you have an electron withdrawing group like nitro, then we would expect that in terms of basicity, this will be more basic, of course, because there is electron donating, okay? And the more electron donating, the more basic. So if you are going to compare, for example, para-methoxy, aniline, no? And then you have para-methyl, okay? Methyl is also an electron donating group, but it is less electron donating than methoxy. So therefore, the more electron donating, the more basic. Okay, so what will happen if they are at different positions? Like for example here, you have para-methyl, para-methoxy, and then you have meta. Take note that the major structural effect of meta is inductive, okay? negative inductive effect. While para is resonance. So this one is adjacent to the lone pair. This will delocalize, delocalize, delocalize. So enhancing the lone pair here. Okay? But for methoxy, the meta position, the major structural effect is electronegativity of oxygen. So that means negative, no? Both can exhibit structural effects. Paramethoxy, oxygen can also exhibit negative inductive effect. Okay? Positive resonance. Okay? Meaning electron donating. Here, oxygen can also exhibit negative inductive effect. It has a lone pair. So this can also exhibit electron donating or positive resonance. However, we said that for methoxy at the para, the electron donating effect is greater, while at the meta, the electron withdrawing effect is greater. So because of that, in terms of basicity, okay, the donating will increase the basicity. Okay, there. Now, what will happen if you have a methyl at the ortho? We said that for acidity of benzoic acid, steric effect can increase acidity, no? Can increase acidity. What will happen if you have a methyl group here? Okay. Say you have NN dimethyl. So you notice it's too crowded. Okay. So if it is too crowded, okay, this methyl group containing the nitrogen will prevent will prevent the delocalization of electron towards the ring. Okay. So if the lone pair cannot delocalize, because this one will rotate. If this group will rotate, the lone pair cannot delocalize. So it means to say that the lone pair becomes more available because it will not disappear from the nitrogen. So the presence of the methyl group at the ortho position will make your aniline more basic. Okay? So meaning if you compare, for example, you have NN dimethyl aniline here, and you have a methyl group here. Okay? If you're going to, you have a methyl group at the meta position, which has no steric effect or crowding anymore. Then the nitrogen will not rotate. So therefore, the lone pair can delocalize. So if it can delocalize, then it is less available. So therefore, this is less basic compared to the methyl at the ortho positions. Okay? So the more electron donating, the more basic. The more electron withdrawing, the less basic. But for acidity, the more electron donating, the less acidic. The more electron withdrawing, the more acidic. Okay? So for your assignments, you're going to submit this to the G drive. Arrange the following in increasing acidity. So from least acidic to most acidic. Okay, that's number one. Okay, so you have those assignments class, no? So before I forget, no? Before I forget class, okay, acidity is also affected by intramolecular hydrogen bonding. Now, this kind of interaction usually happens if the hydrogen bonding occurs at the ortho position for aromatic compounds, like for example here. Okay, this is salicylic acid. It has two ionizable hydrogen, this one and this one. But the carboxylic acid is more ionizable than the phenolic acid. Okay, so we can express this in terms of what you call Ka value or equilibrium constant value. No, so if you recall in your senior high, no, equilibrium constants, okay, are only expressed for weak acids. Anorganic acids are weak acids. So to illustrate that, let us say you have this hypothetical weak acid. A weak acid, unlike HCl, this will ionize in water completely, producing anion and cation. But a weak acid will not. Like for example, acetic acid is a weak acid. It is an organic acid. It will not ionize completely. So what will happen is only a certain amount will ionize. So we use a double arrow to indicate that it will not ionize completely. Only a small amount of that will be converted to acetate ion, and H plus. So the ratio between the concentration of the ionized acetic acid, the product of H plus and the acetate, over the remaining acid that is not ionized, okay, you call this unionized, is what you call equilibrium constant of an acid, okay? And the value of this one reflects the strength of the acid. Look at that. This Ka value, which is the ratio, is directly proportional to H plus. So meaning, the higher the equilibrium constant value, the higher the acidity of the compound. Okay? So, since equilibrium constant are very small values, like in the case of acetic acid, the value is only 1.8. The value for this one for acetic acid is 1.8 times 10 to the minus 5. So that is very small. So this is usually expressed in negative log, okay, to make the value bigger. Just like H plus is expressed in negative log of H plus, which we call pH. So negative log of Ka is called pKa, okay? So if it is expressed in pKa, the smaller the pKa, okay, the more acidic. Just like the smaller the pH value, okay, the more acidic. Okay, so if the pH is 1 to 6, for example, acidic. If it is 7, it's already neutral. greater than 7, more basic. So if the pKa or pH are getting smaller, it means the acidity is getting higher. So if we're going to compare, if we use the word acidity, okay, here is the relationship, no? The higher the acidity, the higher the Ka, no? Pag Ka ang pinag-usapan, the lower the pKa if the value is expressed in pKa, and the lower the pH. Ayan yung relationship, no? The higher the acidity, that means the higher the Ka, the lower the pKa, the lower the pH. So here, if I ask you to compare the pKa, okay, that means the lower the value, the more acidic. But if you use the term Ka, the higher the value, the more acidic. So in terms of pKa, we have two expressions for Ka here and pKa. For Ka, we can have Ka1 and Ka2. For pKa, pKa1, if you express the Ka as negative log of Ka, then that will be pKa1 and pKa2. Okay? So, you have two ionizable hydrogen. So, there are two values for Ka here. The first ionization, which is this one because it is a stronger acid, and the second ionization coming from the phenol. Okay? So, if you're going to compare pKa1, okay, you are referring to the first ionization. So let's compare now, okay, and apply intramolecular concept. So supposing you are comparing two acids, salicylic acid, okay, we focus on the first ionization, so meaning here. So let us say you are using the word pKa. Compare the acidity of ortho salicylic acid and meta salicylic acid. So which carboxylic acid is more acidic? Is it the ortho or the meta? Okay, here the ortho position will be more acidic. Okay, the reason for that one is that when this hydrogen ionizes, okay, this will form negative plus H plus, right? And the more H plus in solution, the higher the acidity, okay? So, the same thing here, this will also ionize. You also have negative here and positive, okay? However, look at the first case. Once the H plus is released, the negative oxygen will be hydrogen bonding with H here because this is partially positive. Okay? A partially positive hydrogen interacting with oxygen is called H bonding. So therefore, the negative is stabilized by the positive hydrogen, leading to neutrality. So therefore, the H plus is released in solution and will not go back because it is already locked with the other H plus here. So obviously that H plus will remain in solution. However, here, if you look at the meta, the hydrogen bonding is very far, meaning it is not effective. Okay? So that's why the negative oxygen is not stabilized by hydrogen bonding. If it is not stabilized, then the H plus has the tendency to return, decreasing the concentration of H plus. So that's why the left is more acidic. And if it is more acidic, that means the pKa is smaller. So that's why you have less than, meaning more acidic because we are using pKa, not Ka. If it is Ka, then that would be Ka1, then that would be greater than. Now let's look at the second ionization, which means pKa2. So we are now referring the ionization of the OH. Okay? So which one do you think is more acidic? The second ionization of ortho or the second ionization of meta? Now look at the ortho. The hydrogen is already locked in the oxygen, so it will be very difficult for the hydrogen to ionize in ortho because it is hydrogen bonded to the oxygen. So we can say that the left is less acidic, meaning higher pKa, because the hydrogen has a difficulty of ionizing because it has hydrogen bonded with the oxygen negative. Unlike in meta, okay, the hydrogen here is free to ionize because it is not locked here. Okay, so take note of that. Intramolecular hydrogen bonding can increase acidity at the ortho position, okay, when it comes to pKa1, but decrease acidity when it comes to pKa2. So here are your assignments. You submit this to the G drive. Okay, arrange the following in increasing acidity, least to most acidic. So you have to arrange the 4. Number 2, you also arrange the 4. Number 3, you arrange these 3. And number 4, arrange the following in increasing basicity, least to most. So you have 1, 2, 3, 4. 5, also arrange basicity, 1, 2, 3, 4. And then number 6, classify the following as aromatic, anti-aromatic, and non-aromatic. Okay, so that's it. This will be your lecture. Okay. Okay, bye.